Welcome back for another private tour at the Western Museum of Flight. I'm Cindy Maka, the director. By popular interest, we have chosen today's topic of Apollo 13 and the Lunar Excursion module that has captured the imagination of many of our members and guests. And by popular demand, we have our go-to technical historian, Ron Gibb.
Hi, I'm Ron Gibb, and welcome to the Western Museum of Flight. Today I'm sitting here next to the space program displays, which shows the Apollo Saturn V rocket, which was used to go to the moon in 1969. And during the 1960s, I was involved in a half a dozen designs on that vehicle, and including the LEM vehicle, which landed on the moon, and I'd like to talk about that LEM vehicle today. NASA decided to use a lunar rendezvous orbit to go to the moon. And what this did, it kept the spacecraft that had to return to Earth, it kept it in orbit around the moon while another vehicle went down to the moon. Now that vehicle was designated the LEM vehicle, the Lunar Excursion module, and it was given to Grumman to build. While they did that, NASA said this has a big risk, and that in order to land safely on the moon and softly, we have to have a rocket engine that can be throttled back to a low level. And at that point in time, there was no engine available in the US to do that. At the same time, they said, we want to use hypergolic propellants that would ignite on immediate contact, so there'd be a low risk of the engine not firing in space. And there was no research been done on that design. So NASA directed Grumman to pursue two design paths with two different engines. So they gave a contract to Rocketdyne, and they gave a contract to TRW, who were both here in the South Bay in Southern California. The design that they used was one by TRW, which is now Northrop Grumman. And that design included a movable ejector, a pentile ejector, that was put in the nozzle of the engine, which allowed it to change the flow rate, and very much like your shower head does in your bathroom, and it adjusts the flow of water coming out. That ejector permitted the 10,000-pound thrust engine that was required to go to the moon to be throttled back to 1,000 pounds. Northrop Grumman design was led by the chief designer, Thomas Kelly, and he was involved in the program from the start. And he came up with a very innovative design. And that design, instead of having one vehicle that went to the moon and came back, he basically came up with a design of having two vehicles. Now what this did, it had three advantages. By breaking the design into two separate systems, they were able to leave the empty fuel tanks and the landing pads from the descent engine and vehicle on the moon. And that greatly reduced the weight required for fuel in the ascent version that went back up to rendezvous with the space capsule. And it reduced the thrust of the engine by a third. So the 10,000-pound thrust engine that was required to go to the moon, it only required a 3,500-pound thrust engine to go up. Instead of 18,000 pounds of fuel on the descent vehicle, they only had 5,000 pounds in the vehicle that went back to join the lunar orbit. The descent stage included the 10,000-pound engine that could be throttled back to 1,000, included the fuel, and was basically 21 feet in diameter when it was stowed in the Saturn V missile. But when the legs were extended to land, it was 30 feet in diameter. And with a total height of 27 feet of the two vehicles, this had a wide path to provide a stable landing on the moon. The upper ascent stage was also the same weight, empty, as the lower stage. They both were 4,700 pounds. And the fuel, as I said, was 5,000 pounds. And it was basically 13 feet in diameter. This is a model of the Saturn V rocket. Basically, it included three stages before the LEM vehicle. The primary stage, the S2 stage, and the S4V stage. And above the S4B stage, the LEM vehicle was stowed behind a fairing that was 21 feet in diameter at the base and 13 feet in diameter at the top. When the vehicle left Earth's gravity and proceeded to the moon, the command module, which is at the top, and the service module separated from this fairing, came out, did a 180, and came back and joined up with the lunar module. And it was in this configuration that the whole spacecraft proceeded to the moon. The LEM vehicle was 33,500 pounds. The space module, the service module, and the command module was 65,000 pounds. The engine on the service module was 20,000 pound thrust, and the descent engine on the LEM vehicle was 10,000. So during the early estimates of going to the moon, NASA estimated that depending on how they did it, it was going to take 1,000 pounds of rocket and fuel to go and put 1 pound on the moon. When you look at the 6.5 million pound thrust Saturn V with the 33,000 pound LEM vehicle, 15,000 pounds of that went to the moon, landed on the moon. So you had a 6.5 million pound vehicle that left with 15,000 pounds going on the moon, so the ratio was 400 to 1. So during the course of the development of Apollo, they were able to reduce the early estimates of 1,000 pounds to put 1 pound on the moon to 400 pounds to put 1 pound on the moon, which was really a remarkable achievement. As I said before, the design team led by Tom Kelly was very innovative in how they developed the LEM vehicle. But there were a lot of challenges and there were a lot of problems, and they made a lot of changes, and they were very late on delivering the first unit. They were almost a year late behind schedule. But in spite of those problems, the LEM vehicle turned out to be one of the most reliable systems on the whole Apollo program. Some of the changes that they made, they started out with 3 legs, they went to 5 legs, they came back to 4 legs. They decided to eliminate the turbo pumps for the engine because they were not very reliable in space. They also decided to eliminate fuel cells and go strictly to batteries to keep the weight down and be more reliable. They eliminated the seats from the LEM vehicle. Both astronauts stood up when they landed on the moon. They eliminated the big windows and went to very small windows, and they completely stripped out all of the trim inside the vehicle, so everything was attached to the skin to keep the weight at a minimum. They also decided to minimize the amount of water and temperature control and oxygen that was available on the vehicle. In the 1960s, I was working at Parker Aircraft, which was located at the entrance of LAX in Los Angeles on Century Boulevard, near where in the same spot that the Marriott Hotel was. They were given the design requirement to design the oxygen regulator for the LEM vehicle. And that design had 2 basic requirements. They wanted to minimize the amount of oxygen that was going to be put in the cabin to minimize the weight, but also because they had planned 2 moonwalks for each landing, the oxygen regulator had to have a high flow rate to replenish and refresh the cabin with oxygen at the right pressure. The pressure of the regulator was set at 4.8 psi. Now that's quite a bit lower than the 14.7 psi that you have here on Earth at sea level. And it's really equivalent to pressure at 30,000 feet. But because of the fact that the oxygen was at 100% and the fact they were in a 0G condition, which required less work, that was the minimum pressure that NASA establishes for us to use. Now, most oxygen regulators, when you have to increase the flow rate dramatically, you use either a coil spring or a bellows spring to control the pressure. And as you increase the flow rate, you have to move the spring up, and you have to increase the load, and you have to increase the pressure, increase the flow rate. Now that causes the requirement for a longer spring and a bigger valve. The concept designer at Parker came up with a very innovative design, and that was a Belleville spring design that was very compact, and he also came up with a concept of a negative spring rate. He was able to use a stack of springs so that as you open up the valve, the spring rate decreased instead of increased, and the pressure stayed the same during the flow rate. And so the difference between the opening pressure and the max flow rate was only 1/10 of a psi. So it was a very efficient regulator. And because of the fact the Belleville springs were very compact, the weight of the body and the whole regulator was very, very small. The final weight of that regulator was 1 pound. So the weight of the oxygen regulator on the LEM vehicle was 1/33,000th. It was a grain of sand in the concept of the whole weight of the vehicle, but it played a vital role. On Apollo 15, 16, and 17, which were the last 3 flights, the moon rover had a piggyback vehicle attached to it, and that was called the Moon Rover, which was nicknamed the Moon Buggy. It basically was a 4-wheel vehicle. It weighed 460 pounds on Earth, which was 75 pounds on the moon. It had a capacity of 1,080 pounds, which included 2 astronauts, a bunch of scientific experiments, and space to put rocks to bring back to the Earth. And it had 4 electric motors. Each motor was a 1/4 of a horsepower, and which was 180 watts, and would drive each motor up to a speed of 8 miles per hour. And with the batteries that they had in the unit, it had a capacity to go 57 miles. Now on the last mission, Apollo 17, the vehicle actually went 27 miles, but the rule of thumb was that they would go the farthest point first, and they would never go anywhere past the point that they didn't have enough oxygen in their suits to walk back to the LEM vehicle. So this enabled the astronauts to greatly expand their exploration of the moon and to collect a lot of variety of rocks and material. Now I'd like to talk about Apollo 13. This mission was well documented in a movie with Tom Hanks in 1995 that talked about the recovery of the astronauts and getting them safely back to Earth. It is deemed to be NASA's finest hour, and the fact, even though there were many failures, the ability of the team to work together to make quick decisions and make the right decisions and to save those 3 astronauts was a remarkable achievement. But also, my feeling is it not only was the finest hour for NASA, it was the finest hour for the LEM vehicle, because the LEM vehicle was the lifeboat to get them back. It was constantly asked to do things it was never designed for, it was never tested and never proven. But with the skill of the astronauts and the support of the team back at Houston, they were able to overcome each problem and successfully return the crew. Now, on the flight to the moon, the Apollo 13 was 55 hours into the mission. It was 8/10 of the distance to the moon, and they had an explosion during a temporary maintenance of the liquid oxygen tank. Now, the number 2 tank blew up. They didn't know what was happening at the time, but all of a sudden they started losing all kinds of electrical power. When the tank blew, it also damaged the second tank, which was supposed to be the backup and supposed to be the redundant system. In addition to that, it damaged 2 of the 3 fuel cells. So all of a sudden they started losing all the electrical power. And so the spacecraft was dying. The decision was made by Houston to move the crew members into the LEM vehicle as a lifeboat. But if they were going to get back, in order to do that, they had to manually shut down the mission computer in the command module, because the only way they were going to get back through the atmosphere safely is if they had that computer managing the spacecraft during the re-entry. And they had never shut down the computer in space, and they never restarted it. So they didn't know if they could, but they did a manual shutdown, and then the crew moved into the space capsule. Now, an immediate decision had to be made because they were coming up to the moon. They had just left the free return orbit trajectory to change the trajectory for the vehicle to go into orbit around the moon. They had to get that uncorrected, reversed, And the only way they could do it, they thought, was with either the service mod engine or the LEM engine. Now, they were reluctant to try to start the service mod engine. It was twice as big as the LEM vehicle, and the service mod was 2/3 of the weight of the space vehicle. They thought it may be damaged, and so they decided not to do that. And that was a correct assessment, because later on they found out the engine was damaged. Now, the second thing they were thinking of is you've got this dead service mod vehicle, which is 2/3 the weight, is 60,000 pounds. If they get rid of that, then it will make it easier for the LEM engine, which is 10,000 pounds, to bring the vehicle back quickly to the Earth. The initial choice was if they fired the service mod engine, they would just do a 180 and go back quickly. So they decided to proceed to the moon and go around the moon. To do that, they had to make that mid-course correction to get back into the free return orbit. So they asked the LEM vehicle engine had no computer. They were going to have to do a manual firing. And normally they would align the LEM vehicle with the star system that they had inside the vehicle, but there was so much debris outside the vehicle they could not line up the stars. So here they had an engine that had never been fired in this role. They were doing a manual firing, and the only way they could orient the spacecraft was to do it with the one star available, and that was the sun. And that was a very crude alignment. They were able to do that firing. They were able to put it back into a free return orbit, and the spacecraft went around the moon and came back. As it was coming back out on the other side, they did a second firing that put the spacecraft into the right trajectory to intercept the Earth. In fact, there were 2 more mid-course corrections done on the way back to the Earth. All 4 of those firings were done manually with a very crude alignment procedure, and all were successful. Now, with the astronauts in the LEM vehicle was much smaller than the command module. And it was just big enough for 2 people with their spacesuits. The height was 7.5 feet to allow the helmet to clear the top. The width was 6 feet, but the depth was only 3.5 feet. So you now had 3 astronauts with 3 90-pound spacesuits inside that capsule and hoping to be able to get back to Earth. The first concern was they did not know if there was enough oxygen, because the design of the LEM vehicle was 2 astronauts on the moon for 45 hours. And here you had 3 astronauts in this same cabin, and it was going to take 90 hours to get back. And the salvation was that the oxygen regulator was able to be operated at a very low pressure and very low limit at a minimum required to recover the astronauts. But the saving grace was there was enough oxygen on board to replenish the cabin twice for 2 moonwalks. And that extra oxygen was enough through the calculations that they made to determine that they could safely return the astronauts and have enough oxygen. The next problem was because they did not know whether they were going to be able to start the mission computer on the command module, and they only had 2 batteries, they decided to cut everything back to a bare minimum to conserve as much power while they worked the problem at Houston. And so as a result, the temperature in the compartment went down to 38 degrees, which was just a little above freezing. And it stayed that way for 3 days. The other problem is they had 2 small tanks of water, and so without the fuel cell that in the LEM vehicle, only batteries, they could not get any water because of burning of oxygen and hydrogen in the fuel cell. So they rationed the water to each astronaut to 1/5 of a liter per day for the rest of the mission. And as a result, the astronaut Fred Hussey got a serious bladder infection and was very ill when he came back to Earth, but they did recover him. The next major crisis they had was the filters for the carbon dioxide was filling up. They had no way of replenishing that because the filters in the command module were a completely different design, It had different fittings, and they could not use them. The team in Houston came up, which is graphically shown in the movie Apollo 13. The team came up with an adapter box they called the mailbox, and they were able to use plastic bags and pages from the checklist that the astronauts had and duct tape, and they were able to make a conversion box that allowed them to take the filters out of the command module and adapt them so they would fit the LEM vehicle, and that was successful in removing the carbon dioxide so they would continue to live. The last major hurdle was how to start the mission computer to re-enter the Earth's atmosphere. And the battery was very low. It took the team in Houston 3 days working out procedures on how to minimize the surge of everything that they had to turn on. And they were able to work out the procedure, and then they relayed that procedure to the astronauts. But there wasn't even a piece of paper in the LEM vehicle to be able to write on. So they had to do this all on radio, by command and verbally, and get them to do it. They were successful in accomplishing that. They then went into the LEM vehicle, into the command module. They were able to start up their mission computer. The minute that came online, that vehicle had spare batteries, and it had spare oxygen, which was used to re-enter the atmosphere. So once they got to that point, they were safe and everything was normal, and they entered the atmosphere at the right position with the last mid-course correction and were successfully recovered. So, and so from a history standpoint, yes, NASA had a finest hour, but the lunar module had a finest hour too, and was the lifeboat that saved those 3 astronauts' lives. So anyway, we're looking forward to this museum opening up, and hope we can see you here to look at our display in the future.